Welcome to Lecture Online, and now let's take a look and see how we use angular measure in astronomy. Let's say, for example, that we're observing Jupiter and its closest large moon Io, and we're wondering how far away is Io from Jupiter. In other words, what is the average orbital distance of Io in its orbit around Jupiter, also known as the semi-major axis of its orbit. And if we know that the distance from Earth to Jupiter when Jupiter is at opposition, in other words, when the Sun, the Earth, and Jupiter all form a single line, and Jupiter is then on the far side there, then we know that this distance here is about 4.2 astronomical units. So let's call this distance from Earth to Jupiter, let's call it big D, and let's say that's equal to 4.2 astronomical unit, realizing, of course, that an astronomical unit is about 93 million miles. And then let's say we go ahead and measure the angle if we take a straight line from the Earth to Jupiter, and then we take another straight line from the Earth to Io. Right? So the distance from the Earth to Jupiter, let's say that is 4.2 astronomical units. Remember, from Jupiter to the Sun, it's 5.2, but when Jupiter is in opposition in a straight line from the Sun, let's put the Sun over here, Earth and Jupiter, then the distance here would be 4.2 astronomical units. Let's say that we measure the angle between Jupiter and Io. So we draw a straight line from the Earth to Jupiter and another line from Earth to Io, when Io is the farthest extent away from Jupiter, because obviously from our perspective, as Io goes around Jupiter, sometimes Io goes directly in front of Jupiter, we can't see it, then it comes back over here, then it's directly behind Jupiter, can't see it, comes over here. So when Io reaches its farthest point away from Jupiter, as observed from the Earth, we measure the angle, and the angle is on 1.863 arc minutes. That's a pretty small angle, and so it's a little bit less than 1/30th of a degree. Knowing the distance to Jupiter, and of course each astronomical unit is 93 million miles, we should be able to figure out the distance between Jupiter and Io, the average orbital distance. And so for that, what we're going to do is we're going to take an example here of a triangle. We're trying to measure the small distance d here, so I'll call this the small distance d. The large distance d is the distance away from the Earth. So big D is 4.2 astronomical units. 4.2 astronomical units. So that's 4.2 times 93 million miles. And the angle we measured to be 1.863 arc minutes. And so the question is, how far away is Io from Jupiter? And the equation we use is this. We can say that the angle divided by 57.3 is equal to the ratio of small d over big D. So wow, where did that equation come from? Well, that is if we use the angle in degrees. So that means we would have to convert the angle from arc minutes to degrees, and we'll do that in just a moment. But you say, well, where did that come from? Well, if you remember back from your geometry days, and you looked at the circle, you know that the circle has radius r, and let's say you make an angle, theta, we can then say that the arc length along the edge of the circle, s, is equal to the radius times the angle theta. And so we could say that the angle theta is equal to s divided by r. Now notice the similarity here. Even though this is an arc length and this is curved, if the angle is very, very tiny, like a very small angle like that, you really can't tell the difference that this is curved. This almost looks like a straight line, so it can be approximated by this triangle that I have right here. And remember, in astronomy, we always talk about very small angles. So this small angle, we can then say that this distance, we call this little d, and we call the radius big D. We can then say that the angle theta is equal to the ratio of small d divided by big D. Now you say, well, wait a minute, where does the 57.3 come from? Well, it turns out that this is in radians. And there's about 57.3 degrees in radians. So if we want to then cut this down from radius to degrees, we have to divide that by 57.3 to get degrees. And so this now becomes our equation. And if we then want to find out what little d is, we can say little d here is equal to the angle theta times big D divided by 57.3. And now let's go ahead and figure this out for our example here. So we had an angle of 1.863 arc minutes, and we have to divide that by 60 to get degrees. So now we convert it from arc minutes to degrees. There's 60 minutes in a degree. The distance, that would be 4.2 times 93 million miles. And the whole thing divided by 57.3 degrees in a radian. Okay, well, I don't need that unit there because the units will cancel out except for miles. So let's try this. So we have 1.863 divided by 60 times 4.2 times 93 million and divide by 57.3 and have a distance of 211,660. So the distance is 211,660 miles, and that would be the orbital radius of Io going around Jupiter. And that's pretty tricky, that's pretty slick here. Think about it. As long as we know the distance to objects and we can see an angle, we can calculate the angle or observe the angle, we can figure out how large things are, how large orbits are, we can figure out how large planets are and things like that simply by using this very simple technique. So big D is the distance to the object we're looking at. Little d is the distance that we're trying to figure out. We measure the angle and we plug into that equation. And remember, this is in degrees, so if we take the measurement and it's in arc minutes, then we have to divide by 60. If the measurement is in arc seconds, then we'll have to divide by 3,600 because there's 3,600 arc seconds in 1 degree, and that's how we find out how big things actually are. So all we need to know is the distance and the angle. Unfortunately, in astronomy, this is usually the hardest thing to figure out. Now, thanks to Kepler, we were able to figure out the distance to planets, but if we talk about an object that we don't know the distance to, of course, we can't use this technique. And we'll find out there's lots of techniques we came up with in astronomy to figure out the distance of things. But if we know the distance, this is the way we find the size of things.